What if everything you thought you knew about reality was just a tiny fragment of the truth? Picture this right now. In some unseen corner of existence, another version of you might be making a completely different choice, living a life that branches into infinite possibilities. This isn't science fiction. It's one of the mind-bending ideas at the heart of quantum mechanics, a realm where particles exist in multiple states at once, where time and space twist into shapes we can barely comprehend. Our universe, vast and mysterious as it is, might just be one thread in a cosmic tapestry woven with countless parallel realities. And today, we're diving deep into 30 theories that shatter everything you thought was solid, stable, or certain about the world around you. Think about the last time you stood under a starry sky, feeling small beneath those glittering lights. Now imagine that each one of those stars, each galaxy, each swirling nebula, could be part of a reality entirely separate from our own. Quantum mechanics doesn't just challenge our understanding, it tears up the rulebook entirely. Particles that communicate instantaneously across vast distances, black holes that might be gateways to other dimensions, even the unsettling idea that reality itself might not exist until we observe it. These aren't wild guesses, they're serious scientific theories debated by brilliant minds, each one more astonishing than the last. So why does this matter to you? Because hidden in these theories are clues to the very nature of existence, why we're here, how the universe began, and whether we're truly alone. Some of these ideas will sound like pure magic, others like nightmares, but all of them will make you see the world differently. From the holographic principle that suggests our reality might be a projection from the edge of the cosmos, to the simulation hypothesis that raises the spine-tingling question: could we all just be lines of code in some advanced civilization's computer? Buckle up, because we're about to journey through the wildest, most awe-inspiring ideas in modern physics, and by the end, you might never look at reality the same way again. Let's start with the theory that twists reality into a kaleidoscope of endless possibilities, the many worlds interpretation. Back in 1957, a physicist named Hugh Everett dared to ask, what if every tiny quantum event doesn't just collapse into a single outcome but splits existence itself? Imagine tossing a coin. In our world, it lands heads or tails, but Everett's math suggests both outcomes happen, each in its own separate universe. Suddenly, every choice you've ever made, every random particle flicker, spawns new realities where every possible version of events plays out. Take Schrödinger's famous cat, simultaneously alive and dead in its box until someone peeks inside. Most interpretations say observation forces one outcome, but many worlds flips the script. The cat lives in one universe and dies in another, with no collapse, just infinite branching. It's as if reality is a cosmic choose-your-own-adventure book where every page turns in every possible direction at once. But here's the catch: how do we test this? Unlike black holes or gravitational waves, parallel universes leave no direct trail. Critics argue it's more philosophy than physics, a sprawling multiverse where every wild scenario exists but none can be proven. Yet supporters counter, the math holds. Quantum mechanics already shows particles in multiple states, why not entire worlds? Whether you find it exhilarating or unsettling, one thing's certain: if Everett was right, somewhere out there, another you is listening to this very sentence and deciding whether to believe it. Now let's step into a theory so unsettling it makes the many worlds interpretation feel almost cozy: quantum immortality. Picture a grim experiment. A person sits with a gun wired to a quantum trigger, one that fires or doesn't based on a random particle's behavior. In most timelines, the gun fires and the story ends, but in the rare branches where it doesn't, consciousness persists. The chilling implication: your awareness might always follow the paths where you don't die, creating the illusion that you've somehow cheated death indefinitely. This isn't just a macabre hypothetical, it's a direct consequence of the many worlds view. If every quantum possibility splits reality, then statistically, there's always a universe where you survive against impossible odds. A car crash, a terminal illness, even old age, your subjective experience would only trace the timelines where you keep going, while other versions of you vanish into silence. Some theorists even tie this to near-death experiences. Those flashes of light or out-of-body sensations could be moments where your consciousness jumps to a nearby surviving branch. Of course, the ethical dilemmas here are staggering. Would anyone have the right to test this? Could it encourage reckless behavior fueled by the twisted hope that some version of me always makes it? And what does it mean for how we value life if death becomes something that only happens to other versions of us? Skeptics dismiss it as a philosophical sleight of hand, arguing that consciousness isn't a ghost hopping between realities. It's rooted in the fragile biology of a single mortal brain. Yet the theory lingers, haunting the edges of quantum debate, because if it's true, then somewhere out there, a version of you is living through every possible close call, every narrow escape forever. And that raises one last eerie question. In a multiverse of infinite endings, how would you ever know when your story really ends? What if the three-dimensional world around you, with its towering mountains, swirling galaxies, and even your own hands, was nothing more than an elaborate illusion? That's the radical suggestion of the holographic principle, a theory that rewrites the very fabric of reality. Imagine the universe as a cosmic movie screen, where everything we perceive in 3 dimensions is actually encoded on a distant 2-dimensional surface. It sounds like science fiction, but this idea emerges from the coldest, hardest math in physics, born from an unexpected place, the study of black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery: black holes have entropy, a measure of disorder, and it's tied to their surface area, not their volume. This was puzzling. Entropy usually depends on how much stuff is inside a system, like the number of ways air molecules can bounce around a room. But for black holes, the real action seemed to happen at their boundaries. Later, Stephen Hawking showed black holes emit radiation, slowly evaporating over time. Combine these ideas and you're left with a cosmic riddle. When matter falls into a black hole, where does its information go? The laws of quantum mechanics say information can't be destroyed, yet black holes seem to erase it. Enter the holographic principle, proposed by Gerard T. Hooft and Leonard Susskind in the 1990s. It suggests the information isn't lost, it's smeared across the black hole's event horizon like data etched onto a celestial hard drive. Just as a hologram stores a 3D image on a 2D film, the universe might encode everything within it, every star, every thought, every law of physics, on a faraway boundary we can't see. String theory takes this further, suggesting spacetime itself is built from tiny, vibrating strings whose patterns project our reality like shadows on a cave wall. But how do we test such an outlandish idea? Fermilab's holometer experiment aims to find out. By firing lasers through incredibly precise detectors, scientists hunt for minuscule pixelation in space-time, hints that reality has a finite resolution, like a digital image zoomed in too far. So far, the results are inconclusive, but the hunt continues. If the holographic principle holds, it would mean the universe is fundamentally simpler than it appears, with all the complexity of life, time, and space emerging from a hidden, flat code. Some physicists resist the idea, arguing it's untestable or overly speculative. Others see it as a potential bridge between quantum mechanics and gravity, 2 pillars of physics that refuse to fit together. Either way, the implications are staggering. If true, you might be nothing more than a fleeting pattern flickering on the edge of an unimaginably vast cosmic canvas. And that raises the ultimate question: if reality is a projection, who or what is holding the projector? What if the universe you're experiencing right now isn't the base layer of reality, but an advanced simulation meticulously coded by some unfathomable intelligence? This is the simulation hypothesis, a theory that's evolved from sci-fi trope to serious scientific debate thanks to philosopher Nick Bostrom. His argument is deceptively simple. If any civilization could ever reach a technological level where they could create conscious simulations indistinguishable from reality, and if they had any desire to run such simulations, then statistically speaking, the odds are overwhelming that we're inside one of those simulations rather than the original universe. Think of it like this: if future humans built 1,000,000 detailed virtual worlds, the chances of you being a real, biological human in the one true reality would be vanishingly small. The Matrix got one thing right: if we are in a simulation, the creators could rewrite the rules anytime. Glitches in quantum behavior, unexplained cosmic constants, or even déjà vu might be subtle hints of underlying code. Elon Musk and Neil deGrasse Tyson have publicly entertained the idea, while skeptics counter that simulating every particle in a universe would require impossible computing power. But what if the simulation only renders what we observe, like a video game loading graphics as you explore? Suddenly, the idea doesn't seem so far-fetched. Now shift gears to something even stranger: Boltzmann brains. Named for physicist Ludwig Boltzmann, this theory suggests that given enough time, random quantum fluctuations in an empty universe could spontaneously assemble a fully formed, self-aware brain. Not attached to a body, not born from evolution, just a lone consciousness blinking into existence, complete with false memories of a past that never happened. Here's the chilling part: in an infinitely old or infinitely large cosmos, Boltzmann brains should statistically outnumber ordinary minds like ours. So why do we seem to be coherent beings embedded in a structured reality rather than drifting, disembodied observers? Some physicists argue this absurd conclusion means our understanding of time or quantum mechanics is deeply flawed. Others propose that the very fact we're having this debate is evidence we're not Boltzmann brains, because statistical flukes wouldn't bother with consistent physics or logical inquiry. Place these two theories side by side, and you get a cosmic identity crisis. The simulation hypothesis frames reality as something built with purpose, even if by unseen programmers. Boltzmann brains suggest existence is a random accident with no design or meaning at all. One implies a hidden architect, the other, chaos so profound that sanity itself is a miracle. Both force us to confront the same unnerving question: how much can we really trust our own experience? After all, whether you're lines of code in a supercomputer or a momentary flicker in the quantum void, the stars above you look just as real. What if every particle in the universe isn't just a fuzzy cloud of probabilities, but has a definite path, a hidden roadmap guiding its every move? That's the bold claim of pilot wave theory, a controversial alternative to the mainstream Copenhagen interpretation of quantum mechanics. While most physicists accept that particles exist in smeared-out superpositions until measured, this theory resurrects an old idea from David Bohm. Invisible, hidden variables secretly steer quantum behavior like unseen currents beneath the surface of a river. The most striking evidence comes from a surprising place: water droplets. In a lab, tiny droplets can bounce on a vibrating fluid surface, skimming along like miniature hovercraft. These walking droplets create ripples that push them in unexpected ways, mirroring the bizarre paths of quantum particles. If you tweak the experiment just right, the droplets even replicate quantum effects like tunneling and interference patterns, phenomena thought to require wave-particle duality. Supporters argue this isn't just a cute analogy. It's a physical model proving particles could have well-defined positions all along, guided by hidden waves we can't yet detect. So why isn't this everywhere in textbooks? For starters, pilot wave theory demands that hidden variables interact instantaneously across any distance, violating Einstein's speed of light limit. It also introduces a layer of complexity many find unnecessary. Why invent unseen mechanisms when existing equations predict outcomes perfectly? The Copenhagen interpretation, championed by Niels Bohr, takes a cleaner approach. Particles don't have definite properties until observed, and that's that. No hidden strings attached, yet pilot wave refuses to fade away. Some theorists see it as a bridge between quantum weirdness and the intuitive, clockwork universe Einstein believed in. Others counter that its math becomes unwieldy when scaling up to complex systems, making it more philosophy than practical physics. But here's the kicker: if hidden variables do exist, they'd rewrite our understanding of determinism, proving reality might be less fuzzy and more structured than we thought, just playing its cards close to the chest. The debate boils down to this: do we live in a universe that's fundamentally uncertain, or one that only pretends to be? For now, the droplets keep dancing, and the question hangs in the air, much like those quantum superpositions Bohm tried so hard to explain. Imagine a quantum particle existing in a blur of possibilities. It could spin up or down, be here or there, all at once. But the moment you reach out to measure it, that delicate superposition collapses into just one outcome. Why that particular result and not another? Quantum Darwinism offers a bold answer. The universe itself is constantly measuring things, not with lab tools, but through something far more mundane: the environment. Picture a tree in a vast forest, its branches splitting endlessly like a fractal. Each split represents a quantum possibility. Now imagine raindrops hitting those leaves. Some branches get weighed down, their paths stabilized by the water's touch, while others remain untouched, flickering uncertainly. In this analogy, the raindrops are photons, air molecules, even the faintest whispers of heat, countless tiny interactions that select certain quantum states to become real, while others fade into the background. This is decoherence in action. The environment isn't just a bystander, but an active participant, reinforcing some outcomes and erasing others until only the most stable configurations survive. But here's where it gets even wilder. Quantum Darwinism suggests that the classical world we see, the solid, predictable reality of apples falling and clocks ticking, isn't the default state of the universe. It's the result of a relentless, invisible filtering process. The reason we all agree on the position of the moon or the color of a stop sign, because those are the states that have been copied countless times by the environment, stamped into existence like a meme going viral across the cosmos. Unstable quantum possibilities get drowned out while robust ones propagate, becoming the shared facts of our everyday experience. Now tie this to consciousness. Some theorists argue that the brain might exploit quantum effects, with neurons acting as microscopic observers, collapsing probabilities into perceptions. Others insist decoherence would smash any delicate quantum states in our warm, wet brains before they could matter. But if quantum Darwinism holds, it blurs the line between observer and observed. Maybe consciousness isn't a special force that collapses reality. It's just another part of the environment, another raindrop nudging the fractal branches toward stability. Critics push back, pointing out that the theory doesn't fully explain why this particular state gets chosen over others, only how it spreads. And if everything is constantly being measured by the environment, why do we still need observers at all? Yet supporters counter that it's the closest thing we have to a rulebook for how quantum weirdness translates into classical order, a cosmic survival of the fittest where the most persistent states become what we call reality. So next time you see a tree swaying in the wind, remember, the universe might be doing the same thing at every scale, shaking out the fragile possibilities until only the sturdy ones remain. And you're both the witness and part of the storm. Deep inside every neuron in your brain, tiny structures called microtubules might be doing something extraordinary, playing host to quantum vibrations that give rise to consciousness itself. This is the bold claim of orchestrated objective reduction, or Orch-OR, a theory dreamed up by physicist Roger Penrose and anesthesiologist Stuart Hameroff. They propose that consciousness isn't just the result of electrical chatter between brain cells, but a delicate quantum ballet happening in these microscopic protein filaments. Picture this: within the warm, wet chaos of your skull, these tubules act like quantum antennas, vibrating at frequencies that somehow stitch together your thoughts, memories, and sense of self. The science here leans on two radical ideas. First, Penrose's twist on quantum gravity, the notion that when superpositions of particles become too large or complex, they don't just randomly collapse, but do so in a way that generates tiny bursts of proto-consciousness. Second, Hameroff's insight that microtubules with their intricate lattice-like structures could be the perfect stage for these quantum performances. Unlike the soupy randomness of most brain matter, these tubules are near perfectly ordered, almost crystalline, potentially shielding quantum states long enough for them to matter. Think of them as nature's quantum computers humming beneath the surface of your awareness. But here's where the controversy ignites. Mainstream neuroscience pushes back hard. Critics point out that quantum effects are notoriously fragile. They usually require extreme cold or vacuum conditions to avoid being destroyed by random thermal noise. Your brain, by contrast, is a warm, jittery place, more like a crowded subway station than a pristine quantum lab. How could delicate superpositions survive for even a fraction of a second amid all that biochemical chaos? Even more damning, no one's found direct evidence of quantum processing in microtubules. Experiments haven't detected the telltale signatures Penrose and Hameroff predict, and most researchers insist classical explanations like networks of neurons firing in sync account just fine for consciousness without invoking quantum magic. Some go further, calling Orch-OR a modern-day phrenology, mistaking tiny structures for grand explanations simply because they're there. Yet the theory refuses to die. Hameroff and allies point to quirks like anesthesia chemicals that erase consciousness by specifically targeting microtubules, not just neuron activity. Others note that certain algae use microtubules to exploit quantum effects in photosynthesis, proving biology can harness such phenomena even if brains haven't been caught in the act. The debate rages on, straddling the line between visionary and fringe, but one thing's certain. If Orch-OR holds even a grain of truth, it would mean your innermost self isn't just electrical, it's quantum, woven into the fabric of the universe in ways we're only beginning to imagine. And that raises a haunting possibility. If consciousness relies on quantum processes, could it exist beyond the brain? Could those vibrations persist in some form after the body falls silent? Penrose and Hameroff don't go that far, but the question lingers like a whisper at the edge of science, unanswered, irresistible, and utterly transformative. We take time for granted, a smooth, unbroken river flowing from past to future. But what if it's not continuous at all? What if time, like light or energy, comes in tiny, indivisible chunks? This is the radical idea behind time quantization, the notion that the universe might tick like a cosmic clock, moving forward in discrete steps called chronons. Imagine watching a movie where the film strip isn't seamless, but made of individual frames so small you can't perceive the gaps. At the smallest scales, reality might work the same way, flickering from one quantum moment to the next. The concept isn't new. In ancient Greece, philosophers debated whether time was infinitely divisible or had a fundamental grain. Modern physics revives this question with a twist. If space and energy are quantized, broken into tiny units like pixels or photons, why wouldn't time follow suit? Theorists propose that chronons could be as brief as Planck time, the smallest meaningful interval in physics, around 10 to the power of negative 43 seconds. That's so short, a single second contains more chronons than there have been seconds since the Big Bang, proving this isn't just philosophical musing. In labs worldwide, scientists wield attoscond lasers pulses so fast they last a billionth of a second to slice time into the thinnest possible slivers. These experiments reveal bizarre behaviors. Electrons, for instance, don't move smoothly between energy levels but seem to jump instantaneously, as if hopping across invisible rungs on a ladder. Could these leaps be evidence of time's pixelated nature? Some researchers think so, arguing that chronons might explain why certain quantum processes appear jarring or discontinuous. Now, layer this with the block universe theory, a mind-bending model where past, present, and future coexist like frames in a film strip. Einstein's relativity already suggests time is flexible, stretching near black holes or speeding satellites, but the block universe goes further. It posits that time doesn't flow at all. Instead, every moment exists eternally, and our sense of moving through time is just an illusion of consciousness. Picture a loaf of bread. The entire loaf exists at once, but we only experience it slice by slice. In this view, chronons wouldn't be ticks on a clock, but fixed, unchanging segments of a static reality. Skeptics counter that quantized time creates more problems than it solves. How would causality work if cause and effect are separated by invisible gaps? And if time is granular, what happens between chronons? Does the universe pause, or is there some deeper mechanism stitching these moments together? Supporters admit the math is thorny, but point to quantum gravity theories like loop quantum cosmology, where spacetime itself is woven from discrete, interlocking loops, a fabric that might naturally include chronons as part of its structure. Whether time is truly pixelated or just appears that way, the implications are staggering. A quantized timeline could rewrite our understanding of free will, destiny, and even the nature of existence itself. After all, if every moment is predetermined in the block universe, do our choices matter? Or are we just passengers watching as the cosmic film unspools one chronon at a time? The answers might lie in those attoscond laser labs, where scientists race to capture time's smallest whispers, and where the universe's deepest secrets could be hiding in the gaps between ticks. What if every time particles become entangled, those spooky, instant connections across vast distances? They're not just linking points in our universe, but stitching together entirely separate realities. This is the wild promise of entangled universes, a theory where quantum weirdness doesn't just defy space and time, it bridges alternate dimensions. Picture two black holes, each the core of its own universe, spinning in perfect sync despite being light years apart. Now imagine they're not just cosmic accidents, but quantum twins, bound by an invisible thread woven through the fabric of the multiverse itself. The math behind this idea comes from the ER=EPR conjecture, a radical proposal by physicists Leonard Susskind and Juan Maldacena. ER refers to Einstein-Rosen bridges, better known as wormholes, tunnels through spacetime that could, in theory, connect distant regions or even different universes. EPR stands for Einstein-Podolsky-Rosen, the famous paradox highlighting how entangled particles instantly influence each other, no matter how far apart they are. The conjecture suggests these phenomena aren't just similar, they're two sides of the same coin. Entanglement might literally be a wormhole in disguise, a microscopic bridge knitting realities together. Think of it like a cosmic game of telephone. In our universe, two electrons become entangled, one spins up, the other instantly down. But in this theory, that connection isn't just a signal passing through space. It's a tiny, twisted thread of spacetime itself, a wormhole so small it's hidden in the quantum foam. Scale this up, and you could have entire universes linked this way, their fates intertwined like pages in a book no one's fully read yet. The implications are staggering. If ER=EPR holds true, then every quantum entanglement event could be a secret handshake between realities, a fleeting gateway to a world where your choices played out differently. Wormholes, often dismissed as sci-fi fantasies, might be as fundamental to reality as gravity or light. And black holes, they wouldn't just be cosmic vacuum cleaners. They could be the universe's way of stitching new threads into the multiverse's tapestry. Of course, skeptics abound. Wormholes are notoriously unstable, prone to collapsing faster than they form. And how do you test a theory that suggests the fabric of reality is riddled with invisible bridges to other worlds? Yet supporters counter that the math is elegant, even beautiful, solving two cosmic puzzles at once. If they're right, then somewhere out there, another version of you is reaching back through the quantum static, separated only by the thinnest of space-time seams, and the only thing keeping you apart is the illusion that you were ever separate to begin with. We think of the vacuum of space as empty, a silent void between stars, but quantum physics paints a far stranger picture. Beneath the apparent stillness, the vacuum buzzes with phantom particles flickering in and out of existence, a seething quantum foam where the very laws of physics might be hanging by a thread. This leads us to one of the most provocative ideas in cosmology, vacuum metamorphosis. What if the vacuum isn't just active but unstable? What if, like water freezing into ice or steam condensing into droplets, the quantum vacuum could undergo sudden, catastrophic phase changes, rewriting the rules of reality itself? Picture a pot of water on the stove, heat it gently, and bubbles form tiny pockets of steam trapped in liquid. Now imagine our universe as one of those bubbles, floating in a vast cosmic pot, where each bubble contains its own unique physics. Some might have stronger gravity, others weaker electromagnetism, or even extra dimensions coiled tighter than a spider's silk. This isn't just speculation, it's a direct consequence of how quantum fields behave at their most fundamental level. The vacuum we know might not be the lowest possible energy state, just a temporary rest stop on the way to something far stranger. The stakes couldn't be higher. If the vacuum decays even in one tiny corner of space, a new phase could erupt outward at light speed, a wall of reshaped physics obliterating everything in its path. Stars, planets, even the atoms in your body would unravel as the old rules vanish. Some theories suggest dark energy, the mysterious force accelerating the universe's expansion, could be a sign of this slow metamorphosis already underway, a faint tremor in the quantum fabric hinting at an impending quake. But here's the twist, we might never see it coming. A true vacuum decay event wouldn't just change the future, it would rewrite the past. The new physics would propagate backward through time, erasing any evidence it ever happened. One moment you're sipping coffee, the next you and your coffee never existed in the first place, replaced by something governed by alien laws. Critics argue this is untestable doomsday fantasizing, but supporters point to the Higgs field, the quantum backdrop that gives particles mass as evidence. Its current state is precariously balanced, like a pencil standing on its tip. The slightest nudge could send it tumbling into a new phase. Experiments at the Large Hadron Collider are probing this fragility, hunting for clues that our vacuum might be more temporary than we'd like to believe. Whether it's a looming threat or just a cosmic curiosity, vacuum metamorphosis forces us to confront a humbling truth. The universe might not be as permanent as it seems. The laws we take for granted could be local customs in a single bubble, one roll of the quantum dice away from vanishing without a trace. And that leaves us with a haunting thought. If physics can change, what else about reality isn't as solid as we think? Forget everything you know about smooth, continuous space and time, because at the tiniest scales, reality might be built from something closer to a cosmic Lego set. This is the bold vision of loop quantum gravity, a theory that dares to rewrite Einstein's spacetime into a fabric woven from finite, indivisible stitches. Imagine zooming in on the universe until atoms look like planets, then zooming further past electrons, past quarks until you hit the ultimate resolution limit. Instead of infinite divisibility, you'd find spacetime itself pixelated into tiny, vibrating loops, each one a fundamental atom of existence. These loops aren't floating in space, they are space. In loop quantum gravity, every cubic centimeter of the universe is a dynamic network of these interconnected threads, constantly evolving like a living tapestry. The math describes them as spin networks, abstract graphs where each node represents a grain of space and each link encodes how those grains relate to one another. Picture a sprawling 3D spiderweb, but instead of silk, its strands carry quantized chunks of area and volume. When the network shifts, when a loop stretches or merges with another, that's gravity in action, not as a force bending a smooth continuum, but as the natural outcome of spacetime's quantum structure rearranging itself. Now contrast this with string theory's approach. Both theories aim to unify quantum mechanics and gravity, but their strategies couldn't be more different. String theory posits that particles are tiny, vibrating strings embedded in a higher dimensional space, like notes played on invisible cosmic violins. It's elegant but demands extra dimensions we've never seen. Loop quantum gravity, by contrast, stays grounded in the 4 dimensions we know, treating spacetime itself as the quantum object. No hidden dimensions, no parallel brains, just the universe's architecture laid bare as a shimmering lattice of loops. The implications are staggering. In loop quantum cosmology, a sibling theory, even the Big Bang wasn't a singular explosion from nothingness, but a big bounce. The spin networks of a dying previous universe could have collapsed to an ultra-dense state before rebounding into our own cosmic dawn. Black holes, too, get a makeover instead of infinite singularities. Their cores might house a knot of loops so tightly wound that spacetime twists into a quantum foam, potentially opening gateways to other regions of the network. Yet challenges remain. While loop quantum gravity elegantly quantizes space, it struggles to explain how smooth spacetime emerges at larger scales. And unlike string theory, it hasn't yet predicted phenomena we can test with current technology. But its promise is undeniable. A universe where gravity isn't a mysterious force, but the rhythm of spacetime's building blocks dancing to the tune of the quantum. Whether those loops are the final answer or just another step toward the truth, one thing's clear: reality is far more modular, far more dynamic than we ever dreamed. What if the future isn't just something that happens after the present, but something that reaches back and shapes it? This is the spine-tingling premise of retrocausality, a quantum theory where effects can precede their causes, and the future might whisper backward through time to rewrite the past. One of the most startling demonstrations comes from the delayed choice experiment, a twist on the classic double-slit setup that forces light to reveal its deepest secrets. Picture a photon speeding toward a detector. In the standard double-slit experiment, photons act like waves when unobserved, creating interference patterns, but collapse into particles when measured. Now add a cosmic twist. What if you wait until after the photon has passed through the slits, when it should have already decided whether to be a wave or particle before choosing whether to measure it? Astonishingly, the photon's behavior changes retroactively, as if your future choice reached back in time to influence its past state. It's like a detective altering a crime scene by deciding after the fact where to look for clues. John Wheeler, the physicist who devised this thought experiment, called it the Great Smoky Dragon of quantum mechanics, a creature whose tail, the past, and head, the future, are equally ambiguous. Modern lab versions confirm this isn't just theory. In 2008, researchers in Australia split photons, sending one half on a short path and the other on a long one. By randomly choosing to measure or not measure the long path photon after the short path photon had already been detected, they found the first photon's behavior depended on the later decision. The past, it seems, is a draft waiting for the future's edits. But how does this square with free will? If future events influence the past, are our choices illusions, scripted in advance by a timeline we can't see? Some interpretations suggest retrocausality doesn't erase free will but expands it. Our decisions might resonate across time, threading cause and effect into a looping tapestry. Others argue it implies a predetermined cosmos where the future is just as fixed as the past, and what feels like choice is merely the universe reconciling its own consistency. The implications ripple outward. In retrocausal models, quantum entanglement could be particles communicating not instantaneously, but backward through time, like two people coordinating outfits by exchanging letters that arrive before they're sent. Even time travelers might not need a DeLorean. If retrocausality holds, every quantum decision could be a microscopic message sent to an earlier version of reality. Of course, skeptics dismiss this as interpretive sleight of hand. They argue delayed choice experiments only appear retroactive because our classical intuition misreads quantum probabilities. Yet the math holds and the mystery lingers. Does time flow one way, or is it a two-lane quantum highway where the future is always quietly rewriting the road behind it? The answer could redefine not just physics, but what it means to make a choice, or whether now is just a fleeting handshake between past and future selves. The Copenhagen interpretation tells us reality solidifies when observed, but who or what truly counts as an observer? This question cracks open one of quantum mechanics' most unsettling thought experiments, Wigner's friend. Picture a physicist, let's call her Alice, inside a sealed lab, measuring a quantum particle. To her, the particle's wave function collapses into a definite state the moment she looks. But outside the lab, Eugene Wigner treats the entire lab, including Alice herself, as a quantum system. From his perspective, Alice remains in superposition, both having seen the particle spin up and spin down until he opens the door to check. So whose observation counts, Alice's or Wigner's? The paradox exposes a fractal nightmare. If consciousness causes collapse, then every observer's reality might be trapped inside someone else's unobserved quantum haze. Now stretch this further. Imagine a VR headset displaying a quantum experiment's outcome. You see a result, but is it your observation that collapses the system, or the programmers who coded the simulation? What if the programmer is also in VR, nested layers deep? Suddenly, the observer effect isn't just about lab equipment, it's a hall of mirrors where reality hinges on an ambiguous chain of awareness. Some interpretations, like cubism, sidestep this by declaring quantum states personal beliefs, not objective truth. Your measurement isn't revealing reality, it's updating your opinion about reality. This eerie dance between mind and measurement resonates with ancient Eastern philosophies. Hindu Vedanta describes the universe as Maya, an illusion that dissolves upon true observation, much like a quantum superposition collapsing. Zen Buddhism's if a tree falls in the forest, koan mirrors Wigner's lab. Does an event exist without a conscious witness? Even Taoist texts hint at a participatory universe where the act of perception shapes the perceived. Yet modern physics balks at placing consciousness center stage. Most physicists argue observation requires no human mind, a photon hitting a detector suffices. But dissenting voices like Nobel laureate Roger Penrose suggest quantum processes might flicker at the edge of biological awareness. Could the brain's microtubules, as in Orch-OR, be tiny observation posts, constantly collapsing reality's probabilities into tangible experience? The debate rages, blurring the line between physics and metaphysics. Whether consciousness is a cosmic architect or mere bystander, one truth emerges. Reality might not be a fixed stage, but a fragile negotiation between the seen and the seer. And that leaves us with a humbling thought. If observation builds the world, what happens when nobody's looking? The world around us seems solid. Dependable tables don't blur into probability clouds when we set down our coffee, and the moon stays firmly in place whether we glance at it or not. But beneath this crisp classical reality lies a quantum undercurrent where particles exist in ghostly superpositions, endlessly flirting with every possible state. So how does the fuzzy quantum realm give rise to the sharp, stable world we experience? Quantum Darwinism offers a startling answer. Reality isn't handed to us fully formed. It's selected through a relentless, invisible competition where only the most resilient quantum states survive. Think of it like evolution in fast forward. In biology, traits that help organisms survive get passed on while weaker ones fade away. Quantum Darwinism suggests something similar happens at the subatomic level. When a quantum system interacts with its environment, whether that's air molecules, stray photons, or even the faintest whisper of heat, countless tiny measurements occur. Most quantum states are fragile, collapsing under these interactions like soap bubbles popping in the wind. But a few states are robust, echoing through the environment again and again. These are the fittest states, the ones that get copied and amplified until they dominate our perception. Recent experiments have brought this idea to life. In a groundbreaking study at the University of Chicago, researchers trapped a tiny particle in a quantum superposition, then bombarded it with controlled environmental noise. The result, the particle's delicate quantum states dissolved almost instantly, leaving behind only the most stable configuration, the one that could withstand the chaos. It's as if the universe has a built-in filter, sifting through infinite possibilities until only the most communicable, most classical versions of reality remain. Visualizing this helps. Picture 1,000 overlapping ripples spreading across a pond after a pebble drops. Most ripples cancel each other out, vanishing without a trace. But a few align perfectly, reinforcing one another to create clear, dominant wave patterns. Those surviving ripples are like the classical states we perceive, the end product of quantum Darwinism's invisible selection process. Now tie this to Schrödinger's infamous cat. Traditional interpretations say the cat is both alive and dead until observed, but quantum Darwinism flips the script. The cat's fate isn't suspended until a conscious observer looks. It's constantly being observed by the environment. Air molecules bouncing off the box, thermal radiation, even cosmic rays all act as tiny observers, relentlessly collapsing the superposition into a single outcome long before a human ever lifts the lid. Critics argue this still doesn't explain why certain states are preferred, only how they spread. Others propose that quantum Darwinism might be a piece of a larger puzzle, one that includes gravity or even deeper layers of quantum structure. Yet the evidence mounts. From lab-manipulated particles to the behavior of complex molecules, the same principle emerges. The universe isn't just there. It's winnowed moment by moment into the stable reality we take for granted. And that raises a profound question. If our classical world emerges from this quantum tournament, could there be other, rarer states lurking just beneath the surface? States too fragile to survive the environment's relentless scrutiny, but real enough to leave faint traces in the fabric of reality. Some theorists hunt for these ghosts in high-precision experiments, hoping to catch reality in the act of choosing before the quantum waves settle and the world we know snaps into focus once more. Black holes have long been cosmic enigmas, swallowing everything, even light, without leaving a trace. But what if they're not quite as bold as we thought? Stephen Hawking's final theory proposed something revolutionary. Black holes might have quantum hairs, delicate filaments of information woven into their event horizons. Picture a black hole not as a featureless pit, but as a cosmic hard drive, its surface etched with microscopic strands encoding the data of everything it's consumed. These quantum hairs wouldn't just be cosmic graffiti, they'd be the solution to one of physics' biggest headaches, the black hole information paradox. Let's unpack why this matters. When a black hole devours a star, a book, or an entire galaxy, quantum mechanics insists that information can never truly vanish. Yet Hawking radiation, the slow leak of energy from black holes, seems to erase that data as the whole evaporates. For decades, this contradiction tormented physicists. If information is lost, the laws of quantum mechanics break. But Hawking's quantum hairs suggest a way out. Imagine two black holes spiraling toward merger in a supercomputer simulation. As they collide, their quantum hairs vibrate like violin strings, imprinting the gravitational waves with faint, telltale notes. These vibrations could carry echoes of everything the holes ever swallowed, a cosmic fingerprint hidden in the ripples of spacetime itself. But here's where things get fiery. The firewall paradox crashes the party. If black holes preserve information in their quantum hairs, what happens to an astronaut crossing the event horizon? Traditional relativity says they'd feel nothing. Spaghettification comes later. But quantum mechanics demands that information can't be copied or cloned, meaning the astronaut's data must either stay on the horizon as hairs or plunge inward, violating quantum rules. The grim solution: a wall of searing radiation at the horizon, incinerating the astronaut instantly. Either black holes are cosmic librarians, painstakingly preserving data in their hairs, or they're surrounded by lethal firewalls. No middle ground exists. The debate rages like the tides around a black hole's maw. Some theorists argue quantum hairs are too fragile to survive a black hole's violent environment, rendering them useless for information storage. Others propose that the hairs aren't on the horizon but buried deeper, like roots beneath a tree's bark. Meanwhile, cutting-edge simulations at institutions like Caltech and the Perimeter Institute are hunting for gravitational wave signatures that might reveal these elusive quantum strands. Whether Hawking's final gift to physics holds up or not, one thing's clear: black holes are no longer the silent, featureless monsters we once imagined. They might be cosmic scribes writing their history in strands finer than spider silk, or they might be guarded by unthinkable fire, burning away the very secrets they're supposed to keep. And that leaves us with a haunting thought. If we ever decode those quantum hairs, what stories might they tell about the universe's darkest corners? What if every fundamental particle in our universe, every electron, every quark, has a secret twin, a mirror image counterpart we've never seen? This is the tantalizing promise of supersymmetry, a theory so elegant it could rewrite the rules of physics while opening doors to infinite parallel realities. Picture the cosmos as a grand dance floor where every known particle has a hidden partner: sleek, shadowy sparkles swirling just out of sight. Electrons would pair with selectrons, quarks with squarks, photons with photinos, each sparkle slightly heavier but perfectly matched to its familiar twin. Why does this matter? Because supersymmetry, or SUSY for short, doesn't just tidy up loose ends in quantum physics. It could be the key to a multiverse bubbling with alternate realities. The math suggests these particles might stabilize the Higgs field, the quantum backdrop that gives particles mass. Without SUSY, the Higgs should be wildly unstable, making our universe's existence statistically absurd. But if sparkles exist, they'd act like cosmic counterweights, balancing the scales so precisely that the Higgs field settles into the delicate state we observe. Here's where it gets cosmic. Minor fluctuations in that balanced Higgs field could spawn entirely new universes, each with different physical laws. Imagine boiling water in a pot. Bubbles form, rise, and pop. Now replace the pot with the quantum vacuum and the bubbles with pocket universes. A tiny nudge in the Higgs field's energy level here, a random quantum flicker there, and suddenly a new universe pinches off, inflating at light speed with its own distinct physics. Some might have stronger gravity, rendering stars fleeting and life impossible. Others might have weaker nuclear forces, preventing atoms from ever forming. SUSY doesn't just predict a multiverse, it suggests one sculpted by an endless froth of Higgs bubbles, each a cosmos unto itself. Yet after decades of hunting, we've found zero sparkles. The Large Hadron Collider, designed partly to uncover SUSY fingerprints, has come up empty. No selectrons, no squarks, no photinos in the debris of its high-energy collisions. Critics call this a crisis, arguing that supersymmetry's elegance might be a beautiful dead end. Supporters counter that sparkles could simply be heavier than current machines can detect, or that SUSY might manifest in ways we haven't yet imagined. Some even propose that particles aren't missing, they're hiding in extra dimensions, or they've already decayed into dark matter, invisible but everywhere. The stakes couldn't be higher. If SUSI is real, it wouldn't just solve quantum riddles. It would mean our universe is one fragile branch on an infinite, bubbling tree of realities. If it's not, physicists might need to rip up decades of beloved theories and start anew. Either way, the hunt continues with upgraded colliders and deeper cosmic surveys probing the shadows for those elusive particles. Because if they're out there, whispering from the edges of detection, the multiverse might be closer and weirder than we ever dared to dream. Ever watched a pot of water, waiting for it to boil, only to find the moment you look away, it finally bubbles over? In the quantum world, something far stranger happens. The act of watching something can freeze it in place. This is the bizarre reality of the quantum Zeno effect, a phenomenon where continuous observation stops a system from evolving, as if reality itself holds its breath under scrutiny. The name comes from the ancient Greek philosopher Zeno, who argued motion was an illusion. Ironically, in the quantum realm, his paradox becomes eerily real. Take radioactive decay. Left alone, unstable atoms will eventually break down, releasing particles at predictable rates. But bombard those atoms with rapid, repeated measurements, and something astonishing occurs. The decay process slows dramatically, as if the particles are reluctant to change under the spotlight. It's not just a theoretical quirk. Lab experiments with atomic clocks, devices so precise they lose less than a second over billions of years, show this effect in action. By frequently measuring the energy states of atoms, scientists can effectively freeze their natural oscillations, stretching time itself into a surreal standstill. The implications are mind-bending. If reality requires observation to crystallize, as the Copenhagen interpretation suggests, could the universe rely on some form of cosmic surveillance to maintain its structure? Some theorists speculate that without a steady drumbeat of quantum measurements from stray photons, cosmic rays, or even conscious observers, the fabric of existence might dissolve into a blur of probabilities. Others push back, arguing the Zeno effect merely reveals how measurement disturbs quantum systems, not that observation creates reality. Visualizing this helps. Picture a spinning coin. While it's mid-air, it's neither heads nor tails, just a whirring superposition. Now imagine snapping photos of it 1,000 times a second. Each flash resets the coin's state, forcing it to remain in that fleeting moment of uncertainty. In quantum terms, the coin never gets a chance to land. Reality becomes a strobe-lit freeze frame. But here's the twist. The Zeno effect isn't just about freezing chaos, it can also accelerate change. The anti-Zeno effect shows that certain types of intermittent observation can speed up quantum decay, like a pot boiling furiously because you keep lifting the lid. This duality suggests observation isn't a passive act but a dynamic force, sculpting reality's flow in ways we're only beginning to grasp. From stabilizing qubits in quantum computers to probing the boundaries of consciousness theories, the Zeno effect blurs the line between observer and participant. It whispers a provocative idea that reality might not be a fixed stage, but a dance where the spotlight shapes the performance. And if that's true, who or what is holding the light? What if every quantum event isn't just a single moment in time, but a handshake between the past and the future? This is the spine-tingling premise of the transactional interpretation, a radical reimagining of quantum mechanics where waves don't just ripple forward through time, they also echo backward, reaching out from the future to shape the present. Proposed by physicist John Cramer in the 1980s, this theory turns the classic view of causality on its head. Picture a photon being emitted by a star. Instead of simply traveling in a straight line to your eye, Cramer's math suggests it sends out an alpha wave forward in time. But here's the twist. Your retina doesn't just passively receive that wave, it sends a confirmation wave backward through time, completing the transaction like a cosmic handshake. Only then does the photon's path solidify into reality. Visualizing this is like watching a negotiation unfold across time. Imagine two people on opposite ends of a dark room, one holding a flashlight. The flashlight beams an offer outward, but the light only becomes real when the receiver signals back, "I accept," their response traveling backward to the moment of emission. This isn't just poetic imagery, it's rooted in the math of advanced and retarded waves, solutions to quantum equations that physicists have known about for decades but largely ignored because they seem to violate our intuition about time. Kramer's genius was realizing these backward-moving waves weren't mathematical quirks, they might be fundamental to how quantum events unfold. Now, tie this to something even wilder: precognition studies. Laboratory experiments have repeatedly shown that human brains can exhibit subtle physiological responses to stimuli before they're actually presented, as if anticipating future events. In one famous series of studies by psychologist Darrell Bem, participants were able to sense erotic images a few seconds before they appeared on screen, with statistically significant accuracy. Skeptics dismiss these results as flukes or flawed methodology, but if the transactional interpretation holds, they might not be so far-fetched. Could our neurons be tapping into those backward-moving confirmation waves, faint whispers from futures that haven't fully crystallized yet? Critics argue that transactional quantum mechanics is needlessly convoluted, adding invisible waves to explain what simpler interpretations handle with measurement alone. Yet supporters counter that it resolves quantum paradoxes more elegantly, like the double-slit experiment, where particles seem to know whether they're being watched. In Kramer's view, the act of detection sends those backward waves, rewriting the particle's history to align with the observed outcome. It's as if reality isn't just built by observation, but by an ongoing dialogue between past and future, a negotiation where every quantum event is a deal struck across time. Whether you find it visionary or outlandish, the transactional interpretation forces us to confront a profound possibility: that the universe might not be a one-way street, but a looping conversation where causes and effects blur into something far stranger. And if that's true, then every glance at the stars, every photon striking your eye, might be part of a handshake stretching across eternity. Dark energy, the mysterious force accelerating the universe's expansion, might not be some exotic substance filling the cosmos. What if it's a glitch in the universe's very code? This is the startling idea behind holographic dark energy, a theory that takes the holographic principle and flips it into an engine for cosmic acceleration. Recall that the holographic principle suggests our three-dimensional reality is actually a projection from a two-dimensional surface at the universe's edge, like a movie playing on a giant cosmic screen. Now imagine that screen isn't static, it's stretching, its pixels straining as the universe expands. Those pixelated edges where the projection phrase could be the source of dark energy's relentless push. Think of it like a video game running at maximum capacity. As the game world expands, the graphics card struggles to render distant details, creating lag or artifacts at the edges of the screen. In this analogy, dark energy isn't a thing, but a side effect of the universe's information limits, a cosmic rendering issue as the hologram scales beyond its original resolution. The math behind this is mind-bending. In 2004, physicists calculated that if the holographic principle holds, the amount of information the universe can contain isn't proportional to its volume but to its surface area. As space grows, that informational boundary stretches thinner, and the tension could manifest as the repulsive force we call dark energy. Here's where it gets eerie. If the universe really is a hologram, its expansion might not be smooth. At the farthest edges, where spacetime's pixels are stretched to their limits, we might find glitches, regions where the projection stutters or distorts. Some theorists suggest these glitches could explain anomalies in cosmic microwave background data, faint irregularities in the afterglow of the Big Bang. Others propose that dark energy's acceleration isn't constant but fluctuates as the hologram's resolution adjusts, like a buffering stream fighting to maintain clarity. Critics argue this is speculative, that linking dark energy to holography is stitching together two mysteries to solve neither, yet supporters point to tantalizing clues. The observed value of dark energy's strength aligns suspiciously well with holographic calculations, a coincidence too precise to ignore. And if future telescopes detect pixel-like patterns in the fabric of spacetime itself, it could be the smoking gun that reality really is a projection, its edges fraying into the void. Whether holographic dark energy holds up or not, it forces us to confront a dizzying possibility. The universe's expansion might not be driven by some hidden fluid, but by the sheer strain of maintaining reality's illusion. And if that's true, then every galaxy racing away from us carries a silent message not about the nature of dark energy, but about the limits of the cosmic screen we call home. Einstein called quantum entanglement spooky action at a distance, two particles instantly influencing each other across vast cosmic gulfs, as if space between them didn't matter. But what if that spookiness isn't just happening within spacetime? What if entanglement is literally weaving the fabric of reality itself? This is the radical premise of emergent spacetime, a theory that turns our cosmic blueprint inside out. The three-dimensional world we move through, the very stage of existence, might not be fundamental. Instead, it could arise from an ocean of quantum connections, a vast network of entangled particles stitching together what we perceive as space and time. Picture the universe as a tapestry. Most theories treat spacetime as the canvas, a rigid, pre-existing grid where particles interact. But emergent spacetime flips this. The canvas is the threads woven moment by moment from countless quantum handshakes. Imagine two entangled electrons. In standard physics, their connection defies spatial logic, but in this view, their bond isn't stretching across space, it's defining space. Every new entanglement adds another stitch to the cosmic fabric, building up dimensions like a 3D printer constructing reality layer by layer. Tensor network models give this wild idea mathematical muscle. These intricate frameworks map how entanglement entropy, a measure of quantum connectedness, scales with system size, mimicking the behavior of spacetime geometry. In simulations, researchers start with abstract quantum systems possessing no inherent space or time. Yet as entanglement grows, structure emerges. Nodes arrange themselves into lattices resembling grids of spacetime, complete with curvature and even approximations of gravitational effects. It's as if gravity itself might be a byproduct of entanglement's relentless networking, a cosmic illusion born from quantum threads pulling taut. One striking example comes from black hole physics. The surface area of a black hole's event horizon, not its volume, determines its entropy, suggesting information is stored holographically. Now combine this with entanglement. When particles near a black hole's edge become entangled with radiation escaping outward, their links might physically stretch spacetime, creating the warped geometry we call gravity. This equals EPA conjecture, linking wormholes to entanglement, hints that spacetime's flexibility isn't just affected by quantum bonds, it might be made of them. Critics argue this is math in search of a mechanism. How exactly do intangible quantum links solidify into the tangible fabric we walk through? Yet lab experiments are inching toward answers. Ultra-cold quantum simulators using atoms trapped in laser grids have replicated miniature spacetime-like structures purely from entangled states. When researchers tune entanglement levels, the system's geometry shifts predictably, as if tweaking the universe's hidden knitting pattern. If emergent spacetime holds, the implications rewrite existence. The Big Bang wasn't an explosion in space, but the birth of space from a primordial quantum soup. Black holes aren't just objects in spacetime, they're knots where entanglement frays, revealing the stitches beneath. Even the passage of time might dissolve into a deeper truth. not a flowing river, but a cascade of quantum updates, each entanglement like a tick of the cosmic clock. So next time you feel grounded by gravity or measure the distance between stars, remember, the floor beneath you, the sky above, might be a shimmering mirage, an exquisite tapestry woven from countless invisible threads, each one a whisper of Einstein's spookiness spinning reality into being. What if the probabilities at the heart of quantum mechanics aren't properties of the universe but reflections of our own uncertainty? This is the provocative stance of quantum Bayesianism, or cubism, a theory that rewrites the rules of reality by putting the observer's beliefs front and center. Picture a high-stakes poker game where each player's bets don't just reflect the cards on the table, but their personal confidence in the next draw. In cubism, quantum probabilities work the same way. They're not objective truths etched into the cosmos, but subjective judgments, bets we place based on our limited knowledge. When a physicist says an electron has a 50% chance of spinning up, they're not describing the electron's inherent state. They're expressing their own degree of belief about what they'll find when they measure it. This clashes violently with deterministic views like pilot wave theory, where particles have hidden, well-defined paths even if we can't see them. For cubists, there's no hidden roadmap, just a fog of personal uncertainty that lifts only when we take a peek. Imagine shining a flashlight into a dark room. The beam doesn't create the objects it reveals, but your knowledge of the room changes instantly. Cubism treats quantum measurements the same way. The act of looking doesn't collapse a wave function into reality. It updates your expectations like a gambler recalculating odds after seeing a new card. The implications ripple through every quantum paradox. Take Schrödinger's cat. In cubism, the cat isn't simultaneously alive and dead in some objective sense. Those labels just represent the observer's uncertainty before opening the box. Once you look, your belief snaps into certainty, but no universal wave function collapses. This sidesteps the need for parallel universes or hidden variables, framing quantum weirdness as a feature of human interpretation, not cosmic architecture. Critics balk at this subjectivity, arguing it turns science into solipsism. If quantum states are just personal bets, how do we explain the astonishing consistency of experimental results? Why do billions of observers agree on the outcomes of measurements if reality is belief-dependent? Cubists counter that shared experiences emerge from similar frameworks of belief, not because nature conforms to a single truth. It's like poker players agreeing on the rules of the game even as they hold private suspicions about each other's hands. Supporters also highlight cubism's pragmatic power. By treating probabilities as personal judgments, it dodges the thorny measurement problem that plagues other interpretations. There's no need to define what counts as an observer or how collapse happens because collapse isn't a physical process, just a mental update. This resonates with fields like machine learning, where algorithms constantly revise predictions based on new data, never claiming to grasp some ultimate reality. Yet the theory leaves haunting questions. If quantum mechanics is a personal guidebook, not a cosmic blueprint, what does that say about the laws of physics? Are they discovered or invented? Cubism doesn't answer this, but it forces us to confront the unsettling idea that science might be less about uncovering absolute truths and more about navigating a universe that stays forever, tantalizingly just out of focus. And in that uncertainty lies its boldest proposition: maybe the quantum world isn't the puzzle, we are. What if every particle you've ever known, every atom in your body, every star in the sky, had a hidden twin, a mirror image counterpart silently sharing our universe? This isn't science fiction, it's the startling premise of mirror matter theory, where parity-violating particles could form entire shadow realms, invisible yet intertwined with our own. Imagine a world where left becomes right, where molecules twist in reverse, and where matter obeys flipped physical laws, a cosmic funhouse lurking just beyond detection. The idea stems from a glitch in nature's symmetry. In the 1950s, physicists discovered that weak nuclear force interactions violate parity, meaning certain particles behave differently when viewed in a mirror. This shattered the long-held assumption that the universe was perfectly symmetrical. If nature allows one asymmetry, why not others? Theorists soon proposed that every known particle might have a mirror partner, identical in mass but opposite in charge and spin. These mirror particles wouldn't just be curiosities, they could clump into mirror atoms, mirror stars, even mirror life, all governed by a parallel version of physics. Now picture this playing out in a particle collider. When protons smash together at near light speeds, a fraction of their energy might briefly conjure mirror particles, fleeting phantoms that vanish without a trace. Detectors wouldn't see them directly, but their presence could betray itself through missing energy or momentum, like a burglar caught on camera by their shadow. Some experiments at CERN have already reported anomalies consistent with these invisible collisions, though the data remains hotly debated. The implications spiral outward. Mirror matter could explain dark matter's gravitational grip without inventing new particles. It might simply be ordinary matter operating by mirror rules, invisible yet omnipresent. Galaxies could harbor mirror solar systems overlapping our own, their planets and suns forever hidden behind a quantum veil. Even eerier, mirror life might have evolved alongside us, unaware of our existence as we are of theirs. Yet challenges loom. If mirror worlds exist, why don't we feel their gravity more acutely? Some models suggest mirror forces are weaker, or that mirror matter clusters in vast, diffuse structures. Others propose that mirror particles decay too quickly to accumulate, and then there's the ultimate question. If these realms are forever separate, how could we ever prove they're real? The answer might lie in cosmic rays or ultra-precise neutron experiments hunting for subtle interactions between the realms. Or perhaps one day, a collider will unleash a mirror particle long enough to leave an unmistakable fingerprint. Until then, the theory remains a tantalizing ghost at the edge of physics, a reflection waiting to step out of the glass. Imagine the smooth, flowing fabric of spacetime not as something continuous, but as a mosaic of microscopic geometric shapes, each one a tiny, shimmering triangle snapping together like pieces in an ever-changing cosmic puzzle. This is the heart of causal dynamical triangulation, a theory that rebuilds the universe from the ground up using quantum geometry. Instead of treating spacetime as an infinitely divisible smooth continuum, this framework suggests it's made of finite, fractal-like building blocks that constantly rearrange themselves. Picture a stop-motion animation where every frame is a new configuration of triangular tiles, each shift rippling causality forward in a dance of structure and chaos. The math behind this is as elegant as it is mind-bending. Researchers take four-dimensional spacetime and slice it into ultra-small simplexes, the geometric equivalent of triangular pyramids in higher dimensions. These aren't static, they dynamically flip their connections, creating a frothy quantum landscape where time and space emerge from the collective behavior of countless tiny shapes. Think of it like a cosmic game of Tetris, where every falling block isn't just filling space but actively defining what time means in that region. The causal part is crucial. Each triangulation respects the light speed limit, ensuring no configuration allows effects to outrun their causes. Visualizing this helps. Envision a kaleidoscope where every turn doesn't just change the colors but rewrites the underlying structure of reality. In CDT simulations, space-time at the smallest scales resembles a wildly fluctuating fractal, while at larger scales it smooths out into the familiar four-dimensional universe we recognize. It's as if the chaos of quantum foam organizes itself into cosmic order through sheer statistical momentum, a self-assembling universe coding its own rules. But simulating this isn't easy. Even with supercomputers, researchers face brutal computational hurdles. every added simplex exponentially increases the number of possible configurations, leaving physicists to navigate a labyrinth of probabilistic outcomes. Early CDT simulations required so much processing power that they could only model universes a few hundred Planck lengths across, smaller than an atom. Yet these tiny digital cosmos astonishingly began to exhibit properties like dimensionality and expansion, hinting that the theory might capture something fundamental about reality's architecture. The implications stretch beyond abstract math. If spacetime is truly built this way, it could explain why we perceive a clear arrow of time. The triangulations naturally favor configurations where cause precedes effect, offering a potential origin for time's relentless forward march. Black holes, too, might look different under this lens. Their singularities could dissolve into complex knots of triangulated space, where geometry tangles into quantum storms rather than infinite densities. Skeptics argue that CDT is just one of many approaches to quantum gravity, with no experimental proof yet. Yet its proponents see it as a bridge between the continuous elegance of general relativity and the fragmented uncertainty of quantum mechanics. Whether it's the final answer or just a stepping stone, one thing's certain. If reality is a cosmic origami of shifting triangles, then every moment we experience is a fold in something far grander, a universe forever reconfiguring itself in the dark. The quantum world thrives on uncertainty, particles spinning in ghostly superpositions, existing in multiple states at once until the moment we observe them. But what if wave functions don't need observers to collapse? What if reality solidifies on its own, like a snowpack suddenly avalanching under its own weight? This is the core of the Gerardi-Rimini-Weber theory, or GRW, a radical take on quantum mechanics where wave functions collapse spontaneously without any human intervention. Imagine a universe where particles occasionally decide their own fate, snapping from fuzzy probabilities into definite states like cosmic dice rolling themselves. Picture an unstable mountainside. Tiny vibrations, shifts in temperature, the weight of a single snowflake might be harmless alone, but pile them up and suddenly the whole slope gives way in a thunderous rush. GRW proposes something similar at the quantum level. Each particle in a superposition has a tiny, random chance to collapse at any moment. For a single electron, this chance is vanishingly small, maybe once every 100 million years. But in macroscopic objects with trillions upon trillions of particles, these mini collapses cascade like quantum dominoes, ensuring that anything large enough to see with the naked eye is always in a definite state. No more Schrödinger's cat suspended between life and death, just classical reality emerging relentlessly from the quantum buzz beneath. The math behind this is both elegant and unsettling. GRW introduces two new constants: the collapse rate, how often a particle chooses a state, and the localization width, how sharply its wave function narrows during collapse. These numbers aren't pulled from thin air, they're tuned to ensure that single particles behave quantumly, while tables, chairs, and cats stay reassuringly classical. It's as if nature has a hidden failsafe, a mechanism that prevents quantum weirdness from scaling up into our everyday experience. But can we test this? Critics argue that GRW's collapses are too subtle to detect directly, like trying to hear a single snowflake land in a blizzard. Yet supporters point to ingenious experiments hunting for faint flashes of radiation that spontaneous collapses might produce. If a wave function truly collapses on its own, it should release a tiny burst of energy, a quantum hiccup echoing through spacetime. Teams in Italy and Austria are now using ultra-sensitive detectors to listen for these whispers, hoping to catch reality in the act of self-resolving. The debate rages on. Some physicists see GRW as an elegant solution to the measurement problem, dethroning observers from their privileged role in shaping reality. Others dismiss it as an unnecessary complication, arguing that decoherence, environmental interactions, already explains why the quantum world seems so orderly at our scale. But GRW's boldness is undeniable. It suggests the universe isn't just probabilistic, it's self-correcting, perpetually tidying its own quantum mess before it can spiral into paradox. And that leaves us with a haunting thought. If particles collapse on their own, what else might reality be doing behind our backs? Quantum Darwinism doesn't just shape the reality we see, it might be the unseen sculptor of the universe's most fundamental laws. Think of the cosmos as a vast, branching tree where each limb represents a different set of physical constants, a unique physics thriving in its own pocket of existence. Gravity could be stronger on one branch, electromagnetism weaker on another, with endless variations sprouting from the quantum foam. But here's the twist, not all these branches survive. Just as evolutionary pressures favor traits that help organisms thrive, quantum Darwinism suggests that only the most stable, self-reinforcing configurations of physical laws endure long enough to build galaxies, stars, and life. Picture a cosmic game of Jenga, where each block represents a fundamental constant: the speed of light, the strength of nuclear forces, the mass of an electron. Tweak one too far, and the entire tower collapses into chaos. Universes where gravity crushes atoms before they form, or where electromagnetism is too weak to bind molecules, never make it past infancy. But those rare, finely balanced configurations where constants align just right to forge complexity become the towering redwoods in the multiverse forest. Their stability isn't luck, it's quantum selection in action. The environment, space, energy, even other quantum states incessantly measures these fledgling universes, reinforcing the robust ones and letting the fragile configurations dissolve back into the quantum haze. Now zoom in on dark energy, the mysterious force accelerating our universe's expansion. Its value is absurdly fine-tuned, a fraction stronger, and galaxies would never coalesce, a whisper weaker, and the cosmos would crumple inward. Quantum Darwinism offers a spine-tingling explanation. Our universe's dark energy isn't a random roll of the dice, but the winner of a cosmological tournament. Countless baby universes flickered into existence with different dark energy strengths, but only those with values permitting structure like ours survived Decoherence's relentless sieve. The others lost to quantum noise like bubbles popping in a cosmic bath. This isn't just philosophy. Simulations of inflationary multiverses show startling patterns. Universes with successful physics tend to cluster in certain mathematical neighborhoods as if guided by an invisible hand. Some theorists argue this clustering isn't coincidence, but evidence of quantum Darwinism operating at the grandest scales. Even the Higgs field, the quantum backdrop giving particles mass, might owe its delicate balance to this cosmic pruning. Universes where the Higgs collapsed into a lower energy state, a fate our own vacuum may still face, could be far more common in the multiverse, but we'd never know because observers like us can only exist in the rare Goldilocks branches where it held firm. Critics counter that this skirts close to tautology. Of course we find ourselves in a universe that permits life. How else could we be here to notice? Yet supporters fire back with a subtle distinction. Quantum Darwinism isn't just anthropic reasoning dressed up. It's a dynamic process where stability emerges from quantum filtering, not passive observation. The constants we see aren't selected because we're here to see them. They're the ones that could persist long enough for us to evolve in the first place. If this theory holds, it reshapes our place in the cosmos. We're not just lucky inhabitants of a finely tuned universe. We're the products of a quantum tournament where the rules themselves were up for grabs. And that raises a dizzying possibility. Somewhere in the multiverse's fractal branches, other sets of laws might have survived, birthing realities so alien we can scarcely imagine them. Not just worlds with different stars or elements, but entire dimensions where time flows backward, causality loops like a Möbius strip, or entropy runs in reverse. The tree of reality might be vaster, stranger, and more ruthless than we ever dreamed, and we're just one leaf trembling in its endless canopy. What if the universe isn't filled with separate, mysterious substances like dark matter and dark energy, but a single, shimmering quantum fluid flowing unseen through the cosmos like an invisible river? This is the bold vision of the dark fluid universe theory, where two of physics' greatest puzzles merge into one elegant solution. Picture galaxies not as isolated islands in empty space, but as knots of visible matter swirling in vast currents of this enigmatic fluid, their motions shaped by its subtle ebbs and flows. Dark matter, that elusive substance holding galaxies together with its gravitational pull, and dark energy, the repulsive force accelerating the universe's expansion, might seem unrelated. One clumps, the other pushes. Yet the math reveals a tantalizing symmetry. The dark fluid model proposes they're two faces of the same coin, different manifestations of a single unified field that shifts behavior depending on its environment. In dense regions like galaxy clusters, the fluid acts like dark matter, exerting extra gravitational glue. In the void between galaxies, it transforms, stretching spacetime outward as dark energy. Think of it like water. Placid pools reflect like mirrors, while churning rapids generate powerful currents. Same substance, different expressions. Modified gravity theories like MND have long argued that dark matter might be an illusion, a sign that Einstein's gravity breaks down at cosmic scales. But dark fluid takes this further, suggesting gravity isn't broken, it's just dancing with something we haven't fully mapped. Imagine tossing a pebble into a pond and watching ripples spread. Now imagine the pond itself is alive, its surface tension fluctuating in response. The ripples behave differently, not because the laws of physics are wrong, but because the medium has hidden depths. Supporters point to odd galactic rotations as clues. Some dwarf galaxies orbit too slowly for standard dark matter models, while others spin too fast. An inconsistency dark fluid could resolve by allowing the fluid's density to vary dynamically. Even stranger, certain cosmic voids, regions nearly empty of galaxies, expand faster than dark energy alone predicts, as if the fluid's repulsive effect amplifies in the absence of matter. Yet challenges remain. If dark fluid pervades everything, why haven't we detected its ripples in labs? Why does it know when to act like matter and when like energy? Skeptics argue it's a clever patchwork, not a fundamental answer. But upcoming experiments like the Vera Rubin Observatory sky surveys could spot telltale distortions in starlight caused by fluid fluctuations, while tabletop quantum sensors hunt for its microscopic vibrations. Whether the dark fluid universe holds up or not, it reframes our cosmic ignorance with haunting beauty. The universe might not be a void speckled with matter, but a living sea, its darkest depths hiding currents that cradle galaxies, steer light, and stretch the very fabric of existence. And we're just beginning to dip our toes in. What if the smooth, continuous space we take for granted isn't fundamental at all, but more like ice forming on a pond, a crystalline structure that froze into place after the universe's fiery birth? Quantum gravity flips our cosmic perspective upside down, proposing that space itself is built from a dynamic, ever-shifting web of connections. A cosmic social network where each friend request between particles defines the very fabric of reality. Imagine the newborn universe not as a singularity, but as a seething chaos of disconnected nodes, a hyperdimensional soup where every point in space could interact with every other point simultaneously. Then, as the cosmos cooled, those frenzied connections began to snap, leaving behind the orderly, three-dimensional grid we recognize today. Think of it like water molecules in steam, wildly mobile, bumping into everything. As steam condenses into water, then freezes into ice, the molecules settle into a rigid lattice. Quantum gravity suggests spacetime underwent a similar phase transition. At energies near the Big Bang, the universe's underlying graph was fully connected, a buzzing hive where distance meant nothing. But as temperatures dropped, links broke and a stable structure emerged, the familiar spacetime we inhabit with its strict rules about locality and causality. The graph in quantum gravity isn't just a metaphor, it's a mathematical framework where each node represents a quantum of space, and each edge defines how those quanta interact. Shatter the edges and spacetime itself shatters. This idea isn't just philosophical. It could revolutionize quantum computing. Today's qubits struggle with decoherence, their fragile quantum states collapsing like sandcastles in a tide. But if space itself is a graph, we might engineer artificial mini-spacetimes where qubits are nodes, their connections immune to classical noise. Researchers at institutions like Perimeter Institute are already simulating graph-based quantum systems, hunting for stability hints. Picture a quantum processor not as a chip but as a pocket universe with custom physics, where information flows along edges we design. The implications ripple outward. If spacetime is a graph, black holes might be regions where nodes rewild, reconnecting into that primordial chaos. The speed of light, just the rate at which information hops between nodes, a cosmic bandwidth limit. Even the arrow of time could emerge from the graph's growing asymmetry, like ink diffusing through paper. Yet challenges loom. How do we test a theory where space itself pixelates only near Planck-scale energies? Some propose hunting for fractured spacetime in ultra-high-energy cosmic rays particles so energetic they might briefly melt the local graph, leaving detectable scars. Others suggest tabletop experiments with supercooled quantum materials that mimic gravity's phase transitions. Whether quantum gravity holds or not, it forces a radical rethink. The universe might not be a stage but a dance, a ceaseless reconfiguration of connections we're only beginning to trace. And if that's true, then every step you take, every star you see, is just a fleeting pattern in an infinite cosmic web, vibrating to a rhythm older than time. The universe as we know it might not be a one-time event, but just one frothing bubble in an infinite cosmic brew, endlessly bubbling into existence in a cauldron of quantum chaos. This is the startling vision of eternal inflation, a theory where the Big Bang wasn't the beginning of everything, but a single eruption in a never-ending storm of creation. Picture a pot of water set to boil. As heat surges through the liquid, tiny bubbles form, expand, and rise to the surface, each one a self-contained pocket of steam floating in the surrounding water. Now imagine that pot is the quantum vacuum, the fundamental fabric of reality, and those bubbles aren't pockets of steam, but entire universes, each with its own unique physics, blossoming into existence before drifting apart forever. The math behind this is as elegant as it is mind-bending. In the earliest moments after the Big Bang, space itself may have undergone a period of hyper-fast expansion called inflation, stretching the universe from subatomic size to cosmic scales in a fraction of a second. But eternal inflation suggests this process didn't stop. It's still happening, just not everywhere at once. Quantum fluctuations act like tiny ripples in the fabric of spacetime, and where those ripples are strong enough, they trigger new bursts of inflation, pinching off fresh bubble universes like soap bubbles splitting in midair. Inside each bubble, inflation slows, allowing matter and energy to condense into stars and galaxies, but outside, the quantum storm rages on, spawning endless new bubbles in an infinite cascade. Think of it like a tree growing in fast forward. The trunk represents the inflating quantum vacuum, stretching endlessly upward, while branches sprout where inflation stutters, each branch a new universe with its own physics. Some branches might have stronger gravity, making stars burn out in seconds. Others might have weaker electromagnetism, preventing atoms from ever forming. A rare few, like ours, strike a delicate balance where complexity and life can emerge. The chilling beauty of eternal inflation is that it doesn't just explain our universe's improbable fine-tuning, it renders that fine-tuning inevitable. With infinite bubbles, every possible combination of physical laws gets tried an infinite number of times. We're not lucky, we're statistical inevitabilities. But how could we ever test such a grandiose idea? Some theorists look for bruises on the cosmic microwave background, the afterglow of the Big Bang, where our bubble universe might have collided with another, leaving faint scars in the sky's heat map. Others suggest that certain properties of dark energy, the mysterious force accelerating our universe's expansion, could betray its origins in the greater multiverse. And if string theory is correct, these bubble universes might not just differ in their physical constants, they could have entirely different dimensions, with some curled up tight like hidden origami folds, while others sprawl in geometries we can't begin to visualize. Critics argue eternal inflation is untestable metaphysics, a cosmic just-so story that explains everything but predicts nothing. Yet supporters counter that it's the natural extension of inflation's winning streak, a theory that's already solved multiple cosmic puzzles, from the universe's eerie uniformity to the faint seeds of galaxy formation. Whether it's the final answer or just another step toward a deeper truth, one thing is certain. If eternal inflation holds, the cosmos isn't just vast, it's endless, a frothing sea of possibilities where every law of physics is just a local ordinance, and every universe is a single note in an infinite symphony. And somewhere out there, in the quantum foam, another bubble might be stirring a universe so like ours or so unimaginably alien that it defies even the wildest dreams of physics. What if the universe didn't just happen to allow life but had to? This is the spine-tingling claim of the final anthropic principle, a radical twist on the idea that the cosmos seems suspiciously fine-tuned for our existence. Forget mere coincidence. This theory suggests observers like us aren't accidental guests in the universe, but inevitable consequences of its very structure. Picture a cosmic lock with a billion dials, the strength of gravity, the mass of electrons, even the density of dark energy. Twist any one slightly and life becomes impossible. Yet here we are in a universe where every dial is set just right. The final anthropic principle takes this further, arguing that this isn't luck, it's a cosmic imperative. Universes that can't produce observers, they might not exist at all. Consider gravity's delicate balance. If it were even a fraction stronger, stars would burn out in a cosmic blink, collapsing into black holes before planets could form. A whisper weaker, and matter would never clump into galaxies, scattering atoms into an eternal void. The same goes for the nuclear forces binding atoms. Tweak them by a hair, and carbon, the backbone of life, wouldn't exist. Even the expansion rate of the universe is a knife edge. A smidge faster and matter disperses too quickly for complexity, slower, and everything collapses in a fiery crunch. These aren't isolated quirks, they're threads in a vast, interwoven tapestry where every stitch must be perfect. But how could the universe mandate observers? Some interpretations lean into teleology, the idea of purpose woven into nature. In this view, consciousness isn't a fluke but a cosmic endpoint, as inherent to the universe's design as galaxies or gravity. Philosophers and theologians have danced around this idea for centuries, but modern physics gives it fresh teeth. If quantum mechanics requires observation to collapse probabilities into reality, could observers be necessary for the universe to fully exist? It's a dizzying loop. No observers, no definite reality, no observers. The final anthropic principle snaps this loop shut, suggesting universes without observers are like unplayed symphonies, potentially beautiful but never actualized. Of course, critics pounce. Enter the multiverse, a frothing sea of infinite universes, each with random physical constants. In this vastness, a handful inevitably hit the jackpot, permitting life by sheer statistics. We're not special, just lucky, the winners of a cosmic lottery with near-infinite losing tickets. This multiverse luck explanation dodges teleology entirely, reducing fine-tuning to a numbers game. After all, if you roll the dice enough times, even the rarest outcome becomes inevitable. Yet the debate rages. Multiverse theories rely on untested, perhaps untestable physics, while teleological hints lurk in quantum mysteries like the observer effect. Even the act of measuring the universe seems to tweak its behavior, as if reality responds to the presence of observers. Experiments like quantum eraser delayed choice tests add fuel, showing that particles can retroactively decide their past states based on future measurements, a eerie hint that time itself might accommodate observation. So where does that leave us? If the final anthropic principle holds, the universe isn't just friendly to life, it's fertile, even hungry for it. Every galaxy, every atom might be part of a grand choreography culminating in consciousness. Or perhaps we're just statistical flukes, temporary sparks in an indifferent void. The answer, or whether there even is one, might lie in the deepest questions physics can ask. Not just how the universe works, but why it works this way, and whether we're here to witness it by accident or by design. From infinite branching realities to the unsettling possibility that we're living in an advanced civilization simulation, we've journeyed through quantum theories that shatter every assumption about existence. The many worlds interpretation paints a cosmos where every choice spawns parallel universes somewhere. Another version of you chose differently, and that reality is just as real as this one. The simulation hypothesis turns this all into code, suggesting our struggles, joys, and even this moment might be lines in some unfathomable program. And holographic theory, it reduces everything: the stars, your hands, even time, to a flickering projection from the edge of spacetime, a cosmic mirage woven from quantum threads. These aren't just thought experiments, they're serious frameworks debated by Nobel laureates and tested in underground labs. Quantum mechanics doesn't just challenge reality, it vaporizes the very idea of a fixed, objective world. Particles communicate instantly across galaxies, black holes might hide gateways to other dimensions, and the universe could be a self-adjusting algorithm where observation stitches facts into being. The deeper we probe, the clearer it becomes. Reality is a placeholder for mysteries we're only beginning to name. So where does that leave us, staring into the quantum abyss where all certainty dissolves? Maybe consciousness shapes the cosmos, or we're accidental flickers in an infinite multiverse. Perhaps the universe is a hologram, a simulation, or something stranger still, a fractal riddle with no final answer. One truth emerges: the more we learn, the less solid the world feels. Now it's your turn. Which theory bends your mind the most? The infinite splintering of the multiverse, the glitching code vibe of simulation theory, or the hologram's haunting suggestion that nothing is as it seems? Drop your thoughts below and keep questioning, because in the quantum realm, the only constant is wonder. Cue montage: shifting fractals, binary rain, cosmic ripples, and Schrödinger's cat blinking between states.